Hello everyone. Today my topic is C13NMR. C13 is the carbon isotope 13 having an abundance of 1.1%. NMR, nuclear magnetic resonance. In our previous class, I have already taken the different types of spectra. First one, undecoupled spectra. We have already done one undecoupled spectra, C13NMR. We have already done broadband or proton decoupled spectra. The third one, that is off resonance decoupled spectra, I am going to take today. Off resonance decoupled spectra. The typical off resonance, the typical proton decoupling technique has the advantage that it simplifies the spectrum. Overhauser effect, carbon atoms with attached hydrogens show increased intensity, and so we get good peaks, good signals. But the major disadvantage is all the useful information, the spectrum becomes, all the useful information is lost. Though proton coupled spectrum provides all this information, the spectrum becomes more complex even for simple molecules due to overlapping multiplets, which are difficult to resolve and analyze properly. Off resonance decoupling technique solves this kind of problem, as it can provide coupling information along with relative simplification in appearance of the spectrum. Now, how this is achieved? It is achieved by irradiating the sample at a frequency close but not coinciding with the resonance of frequency of protons. Normally 1000 to 2000 hertz upfield or 2000 to 3000 hertz downfield frequency of proton TMS is applied. Now the power of decoupling oscillator is held very low to avoid complete decoupling. Now due to this reason, what happens? Vicinal and long range couplings are removed and residual couplings due to geminal carbons are observed. Here we get J1 coupling, J2 coupling, J3 coupling. Now due to this off resonance decoupled spectra, our vicinal and long range, close by and long range couplings are removed. So what remains is geminal couplings. They are clearly observed. So now in this, residual coupling is known as JR. And JR is normally 20 to 25 hertz, which is less than J. JR is the residual coupling and J is the true coupling. It will be around 125 to 300 hertz, which is much more than residual coupling. Now, let us see. So, the equation that is given for this, the equation, we get residual coupling JR is equal to 2 pi, J stands for true coupling. Delta V is the difference between resonance frequency of protons of interest and decoupler frequency. Gamma stands for the gyromagnetic ratio of the process. And B2, the strength of the rotating magnetic field generated by the decoupler frequency. This is the equation that we are going to use. Now, other than that, so what kind of signals we get? They will be line signals. If there is CH3 molecule present, it appears as a quartet. These signals will appear as long lines and they appear as quartets. It will be counted in the form of multiplicity. CH2 will appear as triplets, CH will appear as doublets, and quaternary carbons will appear as singlet. Singlet will just be a single line. When it is a doublet, it will be nearby this kind of lines. Triplets will come something like this. So only line signal will be observed. Now, to make it easier, let us solve this with some examples. Off resonance decoupled spectra. CH3, COO, CH2, CH3. First of all, let us write down the name of this compound. C2H5, it is ethyl. CH3COOH, it is known as acetic acid. Now here it will be called as acetate. So this is ethyl acetate. The molecule that we have is ethyl acetate. Now how do we interpret this off resonance spectra? Let us see. As I told, CH3 will appear as a quartet. We'll refer to this. We will refer to this chart. CH3 appears as a quartet. So we have a CH3 here. It will appear as a quartet. So we'll write it down as Q. Q means quartet. So this is first signal. We are getting one signal here. CH2, we will get it as triplet. First we will write down all CH3 wherever they are present. CH3 is a quartet here. Here also CH3 will be a quartet. Then let us see the next one. CH2, we are not considered about which atom it is attached. So CH2, here it is, as here it is given, it is a triplet. Now this one, this carbon, it is C double bond O. Quaternary carbon. This one is quaternary carbon. C, it is attached to 1, 2, 3, 4. There is no hydrogen attached. Therefore, this is a quaternary carbon. Quaternary carbon, it will show a singlet. So here we are going to get in all 4 signals. 1, 2, 3, 4. So how do we interpret it? OCH3 gives a quartet. OCH gives a triplet. I'm sorry. Double bond O gives a singlet. And finally CH3. While interpreting, we can also write it as double bond O. It gives a quartet. Instead of writing OCH3, we can also write it as CH3. That is also correct. Let us do another example. C2, 2 carbons. Therefore, it is ethyl attached to benzene ring. Benzene ring attached to double bond O's. So, this is an acetate. Acetic acid. I mean, it is an O8. So, benz O8. Ethyl benz O8. Now, ethyl benzoate, let us solve this. This is a carbon, 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 carbon. So, when we observe this carbon, this kind of structure in our BBD spectra or in our other spectra, BBD or the first spectra, undecoupled spectra. In BBD, if we see, if we observe, this is all the carbons are same, so it will be equivalent. But here it is not like that. Carbon attached to this is different. Carbon attached to this is different. Carbon attached to this is different. So what we get? Carbon to this carbon is attached to a single bond and this kind of bond. Let us first solve this. CH3. CH3, according to this, it is a quartet. CH2, according to this, it is a triplet. I believe you can see. Next, this carbon is attached to a double bond and a single bond. So now this carbon, it is a quaternary carbon, therefore it is a singlet. Also, this carbon is attached to double bonds and to the benzene ring. So this kind of singlet is called as ipso carbon. Next we come to this one. This is CH2. This is CH group, CH. So this will be a doublet. This will be CH, therefore it is a doublet. Again this is CH, therefore it is a doublet. These all are symmetrical, so we will not get another signal over here and here. With one signal, both the things will be observed. So therefore in all 1, 2, 3, 4, 5, 6 and 7. 7 signals will be observed. So we have got CH3 as a quartet. OCH2 as a triplet. S ipsocarbon singlet. Two orthocarbons doublet, two metacarbons doublet, and one paracarbon doublet. Two orthocarbons as a doublet, two metacarbons as a doublet, and one paracarbon as a doublet. So in all we will get 7 signals. Here in all we will get 4 signals. Let us solve the next two. Write down the name of this first. 1, 2, 3, 4. Carbonyl attached to this carbon. This is methyl and this is ethyl and this is a ketone. This is methyl, this is ethyl and this is a ketone. So you can say ethyl, methyl, ketone. Let us see the number of signals here. CH3 appears as a quartet. CH2, it will appear as a triplet. C double bond O, quaternary carbon, therefore it will appear as a singlet. Again CH3, a quartet. So in all we have 2 quartets, 1 singlet and 1 triplet. In all we have 4 signals. The next one, let us first write down its name. This is a double bond over here. It is an alkene along with a carbonyl group along with a ketone. So instead of writing down the whole name according to nomenclature, we use the trivial name, that is ethyl crotonoate. Crotonoate. It is ethyl crotonoate. Let us write down CH3. It is a singlet. It appears as a singlet. CH. It is a doublet. CH. Again it is a doublet. This is a quaternary carbon. Quaternary carbon is a singlet. CH2 is a triplet. CH3, it appears as a quartet. So in all, 1, 2, 3, 4, 5, 6. In all, we are having 6 signals. The last one is C13NMR. Last type is selective proton decoupled spectra, which I'll take up in next YouTube live session. Thanks for watching.